Okay, hi everyone. This is track number 3 of ElixirConf 2020, and here with us is Luciano Ramalho. He is presenting us his talk NaturalSet. So welcome, Luciano.
Thank you very much, Edgar. I'm super happy to be here. So let's get started because I have a lot of slides. So NaturalSet. NaturalSet is a set type that I created to demonstrate some very interesting ideas. First, the importance of sets, and also how to implement protocols and streams. Okay, so the talk is going to be about 5 minutes about sets in general. Then I'm going to discuss the MapSet API, and then we're going to see NaturalSet, which is the set type that I implemented to test these ideas. And then we're going to have 5 minutes of Q&A. So why use sets? Basically, like this author said, nobody has yet discovered a branch of mathematics that has successfully resisted formalization into set theory. And clearly, there's a very close relationship between Boolean logic and set theory, right? So let me give you a few examples. Let's say, for instance, you're writing an application that has to publish this page, and you have this sidebar with the new headlines, and then you have the main content area on the right, and you have this card that you need to implement, which says, show newest headlines on the sidebar S, excluding headlines shown in the main content area M. So maybe you would write a loop to, iterate over one or the other lists of headlines. But if Georg Cantor, the creator of set theory, looked at this, he would immediately see that this is a set difference operation. So we are subtracting from the S set, the sidebar set, the main content set, right? Another example is, let's say you have, I created this toy program called RF, the URL is below. And with RF is a command line Elixir application that I can use to search for emojis or whatever Unicode characters by name. And for instance, I have this rule. I want to show a character if all the words in the query appear in the name field of the Unicode database. And Cantor would immediately see that this is a subtest test, right? When you want to see, you have the name set that has 6 words, and you have the query set that has 3 words. And if the query set is completely contained inside the name set, then that's a character that we want to display. One final example, another application that I did playing with Unicode was this other one called Gimel. And Gimel is a web application. So I don't want to scan the whole Unicode database using that logic for the same logic that I showed before, every time that I have a request. So what I did was I created an inverted index, and the inverted index is basically a map where I have, for instance, for the word face, a set of all the characters that have the word face in their description. For the word cat, the set of all the characters that have that word, and so on. So basically, if I need to find emojis with the word cat face eyes, then basically you need to compute the intersection of an intersection, right? The intersection of these 3 sets is the result of the query. And fortunately, Elixir does provide us with a very high-level intersection function for map sets, right? So this is actually retrieving 3 cat faces on IEX using intersections. So the MapSet API is pretty complete. You have the basic operations that every set API needs to support. These are actually so basic that JavaScript implemented them already in ES6. But this is, any set implementation in any language has to allow you to create a set, test whether an element is in the set, put elements in the set, delete elements, get the size of the set, and convert them to lists or provide some other way of iterating, right? Now, this is fine as a basic set of functions for dealing with sets, but this is rather low level. John Bacchus, in his Turing Award lecture in 1977, said, can programming be liberated from the von Neumann style? And basically, in his Turing Award lecture, he was advocating for functional programming. But also, he described this idea of the von Neumann style and the von Neumann bottleneck. And what is that? The von Neumann computer architecture has a CPU connected to memory with a very narrow channel where only one word at a time can traverse, right? So we all know that. But the problem is that we know that so well that sometimes that interferes with our way of thinking. So why is it that JavaScript is such a high-level language, so far removed from the hardware, has a set type that only handles basically set-by-set operations? I mean, element by element operations, right? All of these operations are basically element by element. It's because, I guess, you know, the people who created this set class for JavaScript were thinking in this von Neumann style, thinking tiny elements one at a time. So what I call a rich set API is a set API that has operations on whole sets, like intersection, union, difference. Of course, you can implement that by doing loops with the low-level API, but if you have this high level, then that's where sets become really useful in our daily programming tasks. So MapSet has this very good high-level API with lots of operations between sets. So this is an example of going beyond the von Neumann bottleneck when you do an API. So let's talk about NaturalSet. So NaturalSet is an idea, is a didactic set type that I actually called UintSet until last week. And then I realized that the name that I gave, UintSet, was kind of an example of von Neumann thinking on my part. So I decided to give this more abstract name because it's a set that has the characteristic that it only holds. It's very simple, the implementation, I'm going to show you, but the characteristic is it only shows, it only holds elements that are non-negative integers. So basically the natural set, right? But it wasn't my idea. The idea came from this book. I don't know what you think of Go. I think it's pretty interesting, very complementary to Elixir. But this book is amazing. You know, this is one of the best books about any programming language that I've ever read. It's by Donovan and Kernighan, of course, is the K in Kernighan and Ritchie. And they, in one of the examples that they have in the book, the examples in the book are great. They create this type called the IntSet, which is basically the idea of holding a set. Instead of using a hash table where you have a hash entry for each element, they use a bit vector. So when a bit is set in the vector, that means that the corresponding number is present. I'm going to explain that more in a minute. So let's talk about the NaturalSet implementation, right? It's very short. If I remove the doc strings and the tests, basically it's only 128 lines of code. I published it on XPM as natural_set. And this is basically the whole code. I know you cannot read it, but just to give you a broad idea. And now we're going to see the actual implementation. So it starts with a struct that has only one field, that is bits. This field will always hold a single integer, and it starts with 0, okay? Now, and here I am basically emulating the entire MapSet API, but with this completely different internal representation. while map set is based on maps, so it's based on hash tables under the covers. This is going to be using that bits field as a bit vector. So as you can see, the second case of new enumerable, I created a new set from an enumerable, and I'm using reduce here, and I'm invoking the NaturalSet put function, which I'm going to show in a moment. And then I also have the new with enumerable and a transform function, like mapset has, right? So how do I use one single integer, that bits field, as a bit vector? So this is basically the idea. I'm playing with NaturalSet here on a IEX here, right? So I create a NaturalSet, I get that representation because I implemented the inspect protocol, which I'm going to talk about soon. And if I look at the value of the bits field on an empty set, it's 0, right? Okay, so now if I create another NaturalSet with a 0 element, and I look at the bits field, it says 1. And why is that? So bits is a bit vector. It's actually an integer, but I'm using it as a bit vector. And bit 0, when it's 0, that means there is no 0 element in the set. But when bit 0 is 1, that means there is a 0 element in the set. Let me show another example. If I add the number 1, so I created a new NaturalSet with one element, which is the number 1, all right? So the bits field now reads 2. Why is that? If I convert the bits integer to a binary number representation, I can see there is 1 in the 1 position and 0 in the 0 position. That's because I have a digit 1 I have the element 1 is present, so that's why the bit 1 is set to 1, and I don't have an element 0. So that's why the bit 0 is 0, right? Another example, if I create a NaturalSet with 2 elements, 0 and 1, then the representation of the bits is 1, 1, right? There is 1, meaning that the 0 bits, the 0 bit is 1, meaning that the 0 element is present, and the 1 bit is 1, meaning that the 1 element is present, right? Another example, if I create a NaturalSet with the integers from 1 to 5 as elements, then I have bits, I have 5 bit sets, set, and the 0 bit is 0 because there's no 0 in this set, right? Does that make sense? If you have questions about this representation and the functions that I'm going to show, I hope there will be time in Q&A. So here's another set with just 3 odd numbers, another set with just 3 even numbers. Look at the bits that are set. Here's another example. I have 4 elements in this set. Element 100 is represented by that first one on the left. Then I have a bunch of zeros because I don't have any numbers between 100 and 50. And in the middle, there below the integer word, you see a 1. That's because that's the 50. And then at the end, I have 1, 1 corresponding to the 1 and 0 bits, okay? And of course, this is just, the bits as a string, but this is actually this integer that is being held in bits. And this is very interesting because the implementation of this idea of a bit vector in Elixir is much easier than it was in Go, because in Elixir is not bound conceptually by the von Neumann bottleneck. Our integers can grow as large as memory. They are not 64-bit integers. They are not machine words. So you can have an integer as big as you like. So in this example, this integer here represents a set with those 4 numbers, okay? So that's the crazy idea of using sets represented by bit vectors. So let's see the implementation of the set operations, right? So the first operations are, putting, testing, putting an element, testing whether an element is present, and deleting an element, right? And you can see the source code there. But let's take a look at let's zoom in to the first example. These are all operations that have to do with flipping bits on that bit vector that's stored in the bit field. So and computers are very good at doing that, right? This is a kind of operation that has always been present in digital CPUs forever, and they're highly efficient. So how does this put function work? Basically, what it does is I get the bits field and the element, right? And then I'm going to construct a new natural set to return it, right? And how does that expression there work? Those three less than signs, they are shift left bitwise operator, and the three pipes is the OR bitwise operator. So let's take a look at this step by step. Given, for example, a natural set with the element 0, 4, 5, then the bits field of that set is the number 49, which in binary digits is 110001, right? Okay, so if I want to put the element 2, what I do is I take 1 and I shift it left by 2. So this creates a bit pattern, that's the number 4, which in binary digits is 100, right? So that's the first part there, where you see 1 shift left by the element value, right? The number of the element. Now, if I do a bitwise OR of that bit pattern with the bit pattern that I already had in the bits field, the result is the number 53, which is represented by 110101, right? So basically, this is the natural set 0245, which is the result of adding the number 2, the element 2, to the 045 that we had before, right? So I don't have time to explain all of these operations step by step like I just did, but you can look at the source code. And basically, yeah, I'm using a lot of bitwise operations from the bitwise package that's in the Elixir standard library. Now, the really fun part of this implementation is taking a look at the operations on entire sets. And look at them. This is so great. Intersection, I just do a bitwise AND of the bits of the two vectors, of the two natural sets. Union is just a bitwise OR of the bits of the two natural sets. Difference is a bitwise AND followed by a bitwise XOR. Subset is just, I compute the difference and see if the resulting bits is 0. So that means that the natural set 1 is entirely contained in natural set 2. And this joint is an intersection, and then I see if the resulting bits is 0, which means that there is the intersection is empty, right? So this is really the fun part of using bits to represent sets, because then you can use these bitwise operations. Now, it does get more complicated with the size function. I actually did not implement size because there is this convention in Elixir that a size function should be a constant time function that just returns a size that is already known, pre-computed, is in a field somewhere, right? In this case, I cannot pre-compute, and it doesn't help to have a field with the current length of the set because of the way those operations work. So I actually have to traverse the whole set counting bits. So that's why I needed to follow the convention of calling this function length, because it's a function that operates in linear time, depending on the size. It actually depends on the size of the biggest element and not on the number of elements in the set. But anyway, so length uses these private functions count ones. And I pass to count ones the bits field, the bit vector, and a count, right? So if the bits field is 0, that means that the count is 0, I just return the count. That's the base case of the recursion. The recursive case is where what I do is this on line 67, the expression on the far right is I end the bit vector with 1. So this is effectively testing whether the lowest, the least significant bit is set. That's the bit that I'm looking at right now, right? And if it's set, then the result of this bits ampersand 1, bits bitwise and 1 is going to be 1. So so that increments the count. But if that result is 0, I'm adding 0, so it doesn't increment the count. So, and now I recursively call count ones by shifting left the bits. So this discards the bit that I just counted, and I also pass the current value of the count. So that's how I do a linear search through all the bits and get the count of bits to return the length, right? So now let's talk about protocols. Protocols is a very exciting feature in Elixir. And there's a few predefined, very important, there are few but very important predefined protocols in Elixir 1.10. And it's not so easy to find where they are listed together. If you go to the kernel docs and then you scroll down a lot on this left sidebar, eventually you will find this list of protocols. So those are the protocols that come ready. And I'm going to talk about a few of them. So for instance, the string chars protocol is very important because it's used by the kernel toString function, which in turn is used by IO puts and also by string interpolation in Elixir, right? And the Elixir standard library, for example, does not implement string chars for map set. So you see here in this example that I can use the kernel toString function with an integer, with a list of integers, with an atom, café, I convert it to a string. But if I try to do that with a map set, so map set does implement inspect, map set new, so that shows this representation there, but it doesn't implement toString. If I try to call map set new toString, I mean toString on a map set, whatever its content, then I get protocol undefined error, right? So a protocol is defined, protocols are defined using the def protocol macro, right? So this is the definition. I cut part of the doc string, which is quite long, but the definition of the def protocol string of the protocol string dot chars is just this toString function. And notice there's the toString function header, but there's no body. And that's how you define a protocol. You don't need to define protocols. What you need to do is really to use the protocols that exist in Elixir. That's the best way of using protocols. Leveraging the existing protocols and not so much inventing new protocols. But so what is more often necessary from us is to implement a protocol. And how do we implement a protocol? In this example, that's another repository because this is not part of the NaturalSet implementation. Just as an example, I implemented the string.chars protocol for mapset. And that's an interesting feature of protocols. You can implement a protocol for a third-party struct that is defined in another module that you don't control. In this example, you see I'm using def-impl, so defining the implementation of the protocol string.chars for mapset. And what I'm doing here is implementing the toString function, which basically does what the doc string above shows. If I try to get the toString from a new map set, I get this string of numbers of elements divided by spaces and delimited by curly braces. Okay, so what are the NaturalSet protocols that I implemented? I implemented inspect, which is very important for making IEX easier to use, and also for doc tests. And to implement inspect is easy. You just implement a spec function, and there is a library called inspect algebra that helps you do that. So this is basically a concatenation of the prefix hash NaturalSet less than, then the list of the elements, which is actually generated by using inspect on the NaturalSet converted to lists, and then the close angle bracket, right? Another important protocol is collectible. So a collectible is a protocol that allows you to easily fill data structures. So for instance, in this example here, I show how my new function, which I've shown you before, can be simplified if I implement collectible, which I later did. So instead of using reduce like that, I can just use enum_into. Enum_into uses the collectible protocol. And to implement collectible protocol, you implement an into function. And there's basically this formula that you use, but I don't have time to go into detail now. But you implement into, and I just copied this code from the mapset implementation and simply changed line 112 to use my put function instead of the mapset put function, right? Enumerable is a very important protocol to implement, and to implement it, you have to implement basically 4 functions. I could not implement the slice function because of a convention in the enumerable protocol. That slice should only be used if you can implement it in constant time. I cannot implement slice in constant time with my implementation of NaturalSet. So by convention, I need to return an error tuple in that format there. Finally, let's talk about streams, right? So streams is another great feature of Elixir. But to explain streams, I like to start with a simple Fibonacci example. So this is an implementation of a stream that lazily produces all the numbers of the Fibonacci series forever, actually until memory is exhausted by the representation of the latest Fibonacci number, right? Because these numbers are going to be growing. So basically, you use the explanation here is you use the stream unfold function, which is one of the functions that exist in the stream package to make it easy to implement your own streams. And this works like this. It gets 2 parameters. The first parameter should be an accumulator, which is in this case is a tuple, which is the first pair of the Fibonacci sequence, right? That's how it starts. And the second parameter is a function. In this case, an anonymous function. It gets as the argument, the accumulator, and it returns another tuple that has two parts. The first part of the tuple is the number to be emitted. So in this case, it's A, right, on line 11 there. And the second part of the tuple is actually the next accumulator. And the next accumulator is B and A plus B. That's basically the rule of the Fibonacci series, right? So this is an example of an infinite series. To implement a series that actually stops, then you basically have to return nil when you get to the end. And that signals to unfold that there are no more elements to yield. So how do I stream elements in NaturalSet? I basically implemented this private function called NextOne. And NextOne, it gets as the accumulator the current value of the bits field and the index, which is the element that I'm looking at. When the bits field is empty, that means I return nil because it's over. NextOne is implemented by returning the current index. Oh, NextOne, in the case where the least significant bit is 1. That's what the guard is saying there. So if it's 1, then I yield the element to emit is index, and the next accumulator is the bits shifted, and I increment the index. The last case here is when the least significant bit is not 1, so it's 0. That means I'm not looking at a present element. So instead of returning that tuple, I recursively call the function again by shifting left the bits and incrementing index. So to wrap up, just a few takeaways. If you've never used MapSet, then you should start right now because you're probably writing redundant code. MapSet has a very rich API, including powerful operations with whole sets. Implementing protocols allow custom types to interoperate with core parts of the Elixir standard library, like kernel, enums, and streams. Streaming can be implemented with the help of Streams Unfold and other helpers in the Streams module. And if you want to understand these things, take a look at the MapSet implementation and the NaturalSet implementation, which is a bit simpler, although very limited to handling only natural numbers. Okay, so thank you very much. I think we are out of time. So let's hear it from the organizers.
Thank you, Luciano. This was great. And we are so honored to have you on board with your talk, NaturalSet. So yeah, we are a little short of time and there seems to be no questions. So I will wrap up here and thank you. Thank you again.
Thank you so much, Edgar. Bye-bye.
Ciao. Bye.